In this video, we are going to convert a condensed formula into a skeletal structure. To convert the condensed formula into a skeletal structure, I will first convert the condensed formula into a Lewis structure and then a skeletal structure. Starting with the Lewis structure, the easiest way to solve these problems is to start on the left and connect each atom, mainly carbons, to each other. The hydrogens are grouped according to which carbon they are bonded to, so we add the hydrogens onto those carbons along the way. If we see CH2 in parentheses, that means we have a chain of CH2 groups. If we see any other group in parentheses, it is directly connected to the carbon on its left. The only exception is at the very beginning of the chain. Then the group in parentheses attaches to the only carbon available on the right. Here's a quick guide. CH3 groups need one more bond, so they usually appear on the ends. CH2 groups need two bonds, so they're most likely in the middle. CH groups need three more bonds to carbons or other groups in parentheses connected. A carbon atom itself must always have four bonds. After we have the Lewis structure, to convert the Lewis structure into a skeletal structure, I will start on the end and count the carbons to find the longest parent chain. I will then number the parent chain, looking for the best end to start numbering to have the lowest numbered substituent groups. I will then draw the parent chain for the skeletal structure and number it. I can then add in the substituent groups to the correct numbered carbon. For this compound, I will start with the Lewis structure. For the first one, there's a CH3 group on the end, so I will draw a carbon with three hydrogens attached. Next to it, we have a CH group, and there's a CH3 in parentheses next to it. This tells us that the CH3 is directly connected only to the CH group in the chain. As we are going through this process, we want to make sure that each carbon has four bonds. If we are moving on to the next carbon atom, but the one prior does not have four bonds, we can create double or triple bonds to complete each carbon's octet. Next to the CH group is a CH2, and then a CH group. CH2CH3 is in parentheses next to the CH group, so the CH2CH3 is directly bonded to that CH group. Last, we have a CH3 group on the end. Next, I can number the parent chain to find the longest chain of carbons. We have a 5-carbon parent chain with a methyl on C2 and an ethyl on C4. For naming, I would want the ethyl to be at C2 and the methyl to be at C4 for alphabetical order, because numbering from the right or numbering from the left will give us the same numbers for substituents. I can now draw the skeletal structure. I will start with a 5-carbon parent chain and number the parent chain. I will then put the ethyl at C2 and the methyl at C4. For this compound, I will start with the Lewis structure. On the left, we have CH32CH, which means there will be a CH group directly bonded to two CH3 groups. I draw a CH and place a CH3 on each side of that carbon. That CH is connected to a CH2 group. Next, the CH2 is bonded to CH33, which is a carbon directly attached to three CH3 groups, also known as a torpedo group. As I connect each piece, I check that every carbon has four bonds. If I move on before a carbon reaches four bonds, I will complete its octet as needed. Each carbon has four bonds, so we have completed the Lewis structure. Next, for the skeletal structure, I can find the longest parent chain and number for the lowest substituent positions. There are 5 carbons in the longest parent chain, and if I start numbering from the right-hand side, I will have the lowest numbered substituent groups as 224. Drawing the skeletal structure, I will have the 5 carbons with 2 methyls at C2 and 1 methyl at C4. The skeletal structure is now completed. For this question, I will start with the Lewis structure. From the left, I start with the CH3 group, and I have multiple CH2s, so this indicates a middle chain with no other bonds to those CH2 groups. I will have the CH3 on the end with 2 CH2 groups connected in a chain. Next is a CH group with a parentheses of CH3 after. This tells us that the CH3 group is bonded directly to the CH group in the parent chain. After, We will have a CH2 group and then a C with 3 other CH3 groups bonded to it. Each carbon has 4 bonds, so we have completed the Lewis structure. For the skeletal structure, I look for the longest parent chain. The longest parent chain has 7 carbons, starting to number from the right for the lowest numbered substituent groups. After numbering the parent chain, I see that I have 2 methyls at C2 and 1 methyl at C4. Drawing the skeletal structure, I will have a 7-carbon parent chain and then number the carbons to make sure I have all 7. Then I will add the 2 methyls at C2 and 1 methyl at C4. I have completed the skeletal structure. For this compound, I will start with the Lewis structure. From the left, I have a CH3 attached to a carbon, written as CCH32. That means this carbon is directly bonded to 2 methyl groups and continues the main chain. Next, we have a CH2, and next a CH3. This means that the CH group has a CH3 directly bonded to it. Afterwards, there will be a CH2 and then a CH3 at the end. As I connect, I make sure each carbon has 4 bonds before I move forward. Each carbon has 4 bonds, so the Lewis structure is completed. To convert the Lewis structure to the skeletal structure, I count carbons to find the longest parent chain. The longest parent chain has 6 carbons, and starting to number from the left-hand side will give us the lowest numbered substituent groups of 224. Drawing the skeletal structure, I start with 6 carbons and number the parent chain. I then put 2 methyls at C2 and 1 methyl at C4. The skeletal structure is now complete. For this compound, I will start with the Lewis structure. From the left, I start with the CH3 group and then connect it to the CH2 group. Next, I have 2 carbons with no hydrogens bonded. Something different is happening here. We do not have enough hydrogens to make 4 bonds total for those carbons. Each carbon has a CH2 group on either side. The first carbon is missing 2 bonds, and the second carbon is missing 2 bonds. If I triple bond those 2 carbons together, there will be a total of 4 bonds for each of those carbons, and then we can continue. We have the CH2 group and then a CH group with 2 CH3s connected to it. Each carbon has 4 bonds, so we have completed the Lewis structure. For the skeletal structure, I will find the longest parent chain. The longest parent chain has 7 carbons, and if I start numbering from the left-hand side, I will have the triple bond at the lowest numbered carbon possible in the parent chain. Drawing a triple bond in a skeletal structure requires a straight 180-degree bond angle coming out of the triple bond on each side. It can be easiest to start drawing the triple bond first, so I will start with the triple bond. After I draw the straight line coming out of the triple bond, I can start the zigzag pattern again. On the left, I have 2 more carbons in the parent chain, so I will have 1 straight carbon and then a zigzag. On the right-hand side, I have 3 more carbons, so 1 straight carbon and then 2 zigzags. I can now count the skeletal structure to make sure there are 7 carbons total. There are 7 carbons total, so I will add the methyl at C6. The skeletal structure is now complete. For this compound, I will start with the Lewis structure. From the left, I start with the CH3 group and connect it to a CH group. Next, I have another CH group and then a CH2 group. These 2 CH groups do not have 4 bonds total. They are each missing 1 bond. I can double bond the 2 CH groups together so they have 4 bonds total. Last, I have a carbon written as CCH33, which is a carbon attached to 3 CH3 groups, also known as a tert-butyl group. Each carbon has 4 bonds, so our Lewis structure is complete. For the skeletal structure, I will find the longest parent chain. The longest parent chain has 6 carbons, and when I number a parent chain with a double bond, the double bond takes priority over the substituent groups. Numbering from the left-hand side to have the lowest numbered double bond, it will be 1, 2, 3, 4, 5, 6. The double bond starts at 2, and we have 2 substituents at 5. Drawing the skeletal structure, there will be 6 carbons in a zigzag pattern with a double bond at C2 and 2 methyls at C5. The skeletal structure is complete. For this compound, I will start with the Lewis structure. From the left, I have a CH3 connected to CHOH. This tells us that the OH group is directly connected to CH in the structure. Then there is a CH2 and a CH3 The two CH3s in parentheses will be directly bonded to the carbon. Next, there is a CH2 and then a CH3. All groups have 4 bonds, so we have completed the Lewis structure. For the skeletal structure, I will find the longest parent chain. We have now introduced a functional group into the structure. Functional groups take priority for numbering the parent chain when comparing them to substituents. There are a total of 6 carbons in the longest parent chain, and starting to number from the left, OH will be at C2 and 2 methyls at C4. Drawing the skeletal structure, there will be a total of 6 carbons with an OH at C2 and 2 methyls at C4. The structure is complete.